Good morning, everybody. Thanks to the organizers, that means Cedric and Kuntal, for giving me a chance, and thanks to CEFIPRA also for getting me involved. And thanks to all of you who have come all the way from India. And I'm an outsider. I mean, I don't represent anybody. I can say anything I want. So whatever is going to be said is my version of things. And of course, you are free to ask any questions also. But I'm representing here WWRF, and we'll talk about that 5 minutes if we have time in the end. So I'm going to talk about what is happening in ITU. ITU is International Telecommunication Union, who has been doing a lot of work in 3G, 4G, 5G, and now in 6G. And I'm going to represent several things about the work being done in ITU and what is has been its role in the definition of IMT. IMT, nothing to do with IMT, it means telecom. It is International Mobile Telecommunication System. And 5G is what is 6G is actually enhancement of 5G towards 6G. And then there are so many different technologies which are being discussed in ITU. So there is beyond 100 gigahertz terahertz transmission technologies. There is RIS, Reflective Intelligence Services. Then there is NTN, so non-terrestrial networks and integration with the terrestrial networks. Then of course there is AI. AI for AI means artificial intelligence for air interface and other uses of AI. Then we are talking about integrated sensing and communication. Then we are talking about new waveform, which can be OTFS. And then there is dynamic spectrum management, and there is networking technology, things related to architecture and Open RAN and so many things. The international scene of research and technology evolution is very, very active. There is a lot. I can say I can continue for 2 hours, but the point is that here looking at the audience and especially our guests from India, most of them are working in the physical layer. So I'll be concentrating only on the 4 different technology blocks, which are shown here in bold letters. That is beyond 100 gigahertz, RIS, NTN, and then of course AI for the air interface. That's where we start. That gives you a better picture of what has been ITU doing about the evolution of different generations. And maybe most of you have already seen these diagrams multiple times. So we have the second generation, which was really made global. It is GSM. It was just cellular, reuse of frequencies. And it was mainly for voice communication and voice communication to mobile users. Then came the 3G, and 3G was up to 2 megabits per second of data transmission, and we started working with video transmission and all that. And ITU is known for producing some representations, like for 3G, they produced this thing called the Venn diagram, which shows how the data rate and coverage are related, or how the data rate and coverage have to be related if you want to list your system as a 3G system. Okay? Now, by the way, the 3G system in ITU was called IMT 2010. Okay? And then came 4G, which is LTE, and that was listed IMT 2020. 4G was listed IMT 2020, and 5G was listed IMT 2020. And IMT 2020, 5G, the representation diagram which ITU gave. So anyway, you can see this triangle, and maybe you have seen this triangle also very much. So in 4G, it was the Venn diagram. I said something wrong earlier. And in 5G, it is this triangle. The 4G was very much for the data, and 5G is also for the data, but with applications other than just mobile and video transmission to mobile use. Okay, and 5G started a lot of work on what is called vertical sectors, and that is this triangle which shows what are the different scenarios of application of 5G, and there is this spider diagrams which shows what are the different capabilities of 5G, that different performance metrics have to be fixed. Okay, and the main purpose of doing standards is standards are essential for the identification of spectrum, in which the different technologies can be implemented, different generations can be implemented, and then standards ensure what is called network interworking, subscriber interworking between different manufacturer products, and it is good for economy of scale, and standards are supposed to make arrangements for subscriber roaming and for security of communications and security of the subscribers also. Okay, so this was what was done in 5G, and we are going to see what is going to be 6G. And before that, description of what is of interest to ITU. So what is ITU? ITU is the United Nations specialized agency for information and communication technology. Their basic objective is to establish standards so that we can ensure interworking, and at the same time, and mainly at the same time, make sure that the frequencies bands for which these systems are going to be working can be identified and accepted everywhere. And ITU works with the different bodies, and the two most important bodies are World Radio Conference, WRC, and the Radio Communication Study Groups. And what is Radio Communication Study Group is shown in this diagram. As you can see, there is Study Group 5, and there are several working parties, and the working party of interest to IMT systems is IMT WP5D. So in the WP5D, in study group 5 is supposed to be doing the standardization work for IMT systems. So they have done it for IMT 2010, they have done it for IMT 2020, and now they are busy doing it for IMT 2030, which is supposed to be 6G. And all types of, all these committees, all these working parties have membership from different organizations. There are government bodies, there are academia, there are the sector members like WWRF is a sector member, and there are SDOs. What is SDO? SDO is Standard Development Organization. Okay, and all these people are free to make contribution, participate in the meeting, and of course the results, the outcome is always given on a consensus. So coming back to 5G, so these are the spider diagrams. I'm sure you have seen all these many times already, and you know there are things like peak data rate, the spectral efficiency, mobility, latency, and so on. Okay, in 5G there were certain values, certain key performance indicators which are fixed, and there are some very stringent things to be respected, like the user density for very high density IoT applications. Then there was the latency for very mission critical systems. And then there is, of course, the bit rate which the user can fix, which user can get for mobile broadband applications. And in 6G, all these things are supposed to be enhanced. So 6G is being characterized, actually IMT 2030 is being characterized by performance enhancement for IMT 2020 use cases. And then, as I mentioned earlier, there are new technologies with technology capabilities like integrated sensing and communication, AI for AI, and of course NTN, the non-terrestrial networks for universal connectivity. As you can see in this diagram, so this triangle of 5G, IMT 2020, has been stretched out to make a hexagon, and that shows the new KPIs for 6G. And in addition to these KPIs, there are 4 overarching themes which the 6G is supposed to respect. And those 4 overarching things are related with what is called the Sustainability Development Goals established by UN. And 5G was like, we make sure that all the vertical applications work. You know, we have spectrum and we have key performance indicators. In addition to that, 6G is supposed to make sure that all these sustainability development goals are achieved. And one of those a few of those sustainability development goals are listed here. One is sustainability in terms of energy consumption. One is connecting the unconnected, because there is a lot of people still who don't have accessibility to network. And then there is the use of ubiquitous intelligence. And then there is security and resilience, both for the network as well as for the users. And there are certain other sustainability goals. There are 17 of them, but I don't think I have the time to go through those things. Okay, so this gives you a better picture. I mean, these things, you know, are the KPIs for 5G, IMT 2020, and capabilities which IMT 2020 5G was supposed to respect. And you can see that new capabilities, the earlier capabilities of IMT 2020 have to be enhanced to achieve the capabilities required for IMT 2030, 6G. And then there are additional capabilities which IMT 2030, 6G is supposed to have. And from here, of course, I can't go into detail. You can look at these diagrams. This is available everywhere. And actually, you can find all these diagrams in the reports, which are the documents which are freely accessible, established by ITU. And there is a report 2516 and 2160, which give in detail all the information. What I need to say here is that you can see that, for example, for peak data rate, we were talking about 20 gigabits per second for IMT 2020, but in IMT 2030, we are supposed to go up to 200 gigabits per second. And of course, there are something very important again somewhere is the latency. In 5G, I think everybody knows, we are supposed to respect latency of less than 1 millisecond. Here people are talking about 0.1 to 0.5 millisecond of latency, okay? And of course, mobility, it was 200 kilometers per hour. Here it is 6G, it is supposed to be 500 kilometers per hour. I don't know what they will do with it, but I mean, everything is completely stretched out. And then, as I mentioned, that there is additional capabilities, like we are talking about positioning with an accuracy of 1 to 10 centimeters. Okay, now IMT 2030 network will be deployed in many frequency bands. People are talking about less than 7 gigahertz, as well as millimeter wave, as well as terahertz, and like going above 100 gigahertz. And then these gigahertz, these systems, these applications require very high bit rates. Like we were talking about 200 gigabits per second. You can't achieve that in 1 megahertz of spectrum. And you need maybe 200 megahertz of spectrum, because if you are going, and that you can find only very high in the frequency. Okay? So we are talking about very high bit rate applications, like for holographic transmission, and then we need very high signal bandwidth, and that is found only somewhere very high in the frequency band, like we are talking about beyond 100 gigahertz of spectrum band. Okay, and so that brings me to the some detailed explanation of the next subject. So first subject is terahertz communications. Now terahertz communication is being studied quite a lot, and the first thing all of us radio guys, they want to always look at what does the propagation channel look like. The terahertz propagation channel looks like something like this. That means you have frequency, and then you have the path loss in the frequency. From this schematic, you can see that there are certain, you can say, sweet spots where the attenuation is nearly flat, and then there are peaks, and those peaks of absorption come due to particles, due to rain or other particles in the atmosphere, and these peaks, they show that there is very high attenuation, very high path loss, and you can see that in this curve, at these frequency band, the peaks are not very sharp, but as you go into this curve, in the same frequency band, you see those peaks which are higher. So actually what it shows is that for the blue curve, we are talking about a link distance, transmitter to receiver distance of 1 meter, and there you get a flat zone of something like 540 gigahertz of band which you can use. And as you increase the link distance, the band which you can use without deep, I would say, peaks of attenuation, peaks of absorption, that changes. Okay? So the channel, the available bandwidth for good usage depends on the link distance. And then if you are working in this band of frequencies, you can use 540 gigahertz, so you can design a modulation and a symbol rate accordingly. But if you go to this frequency, then the available band and the available symbol rate you have to use is different, smaller. Okay? That's because there are all these absorption peaks due to particles and all that. So this thing has been widely studied, and there have been lots of experimentation done everywhere in the world. And here I just give you an example. And by the way, all these slides are copied from somewhere. So you have the reference, which is given below. but none of this is my work because I don't work. Okay. Now, so one of the records which has been recently established by University College London, is this transmission exploiting different bandwidths available in different frequency regions, and they have shown a net bit rate transmission of 812 gigabits per second in a channel bandwidth of 145 gigahertz. Okay, so they take some channel bandwidth in one frequency band, they design modulation accordingly, and then you can see from the top schematics that in certain frequency band they exploit both the vertical and horizontal polarization. Okay, and you can see sometimes there is 26 QAMs, sometimes there is only 16 QAM, and of course, as you go high in the frequency, it is not simple to design modulators and demodulators if we have a very high symbol. Okay, so but this is something which is existing, which has been published in this reference which is given there. So I think that is kind of record performance of use of terahertz frequencies. Okay, then there is another record by doing channel grouping. You can achieve by grouping 20 channels of 2.16 gigahertz each. You can get up to 100 gigabits per second of transmission. And then I heard of another record which is done by Tsinghua University in Beijing, which says, and they claim that they have done 80 gigabits per second of transmission in a line of sight channel at terahertz frequencies, but 80 gigabits over 100 meters. Okay, you see, we were talking about 1 meter, 2 meter, 10 meter channel distance, but they claim that they have done this 80 gigabits per second over 100 meters. And I made a quick calculation. If you do a receiver which has 20 dB antenna gain and it's only BPSK modulation, you need something like 500 watts of EIRP, if you make a quick calculation. Okay, so I don't know how far it is true, but I have discussed with the professor. I saw him and he said, yes, you are right. That's the kind of EIRP we are using, and I don't know how far it is feasible at terahertz frequency, and if such an EIRP is lethal for health or not. I have no idea, Okay, so then just to finish this subject, we have seen that very recently the Telecom Regulatory Authority of India has launched a consultation for identification of terahertz spectrum in India. But at the same time, it is for my Indian colleagues. I have no idea of the state of research or industrial usage of terahertz frequencies in India. But I can, just to come back to ITU, I can tell you that the Indian delegation is participating in all the work in the development of this report on beyond 100 gigahertz transmission in ITU, in WP5D meeting. Okay, now, and all this is not just theory, not just paper. There is already technology available. The different semiconductor technologies which can be used in different frequency bands have been already identified. There is once again an ITOR report available here, and then there are certain very different technological blocks like antennas and how you are going to integrate those antennas into, for example, a mobile. All these things are really available. I mean, they are available at experimental scale. They are not available yet at industrial scale, but this is not just theoretical work. And then we can see that terahertz is being used for different applications, and the diagram shows you a little bit what are the different use cases for different frequency band, and what is going to be done in 5G or what is going to be done later on in 6G is all mentioned here. Okay. Now, terahertz has been, and all this is included in the ITOR report, has been identified to be usable for pencil beam forming, for massive MIMO application, and like for holographic MIMO application, and also along with the reflective intelligence surfaces. And of course, all these things for ultra accuracy localization, ultra precise positioning, and simultaneous imaging and mapping, and that is coupled with gesture and movement detection. This is applicable for security applications, for healthcare. People are talking about remote surgery and all those things. Okay. Now, from here, you can see that terahertz is a very useful frequency band, and people think that coupling it with RIS is going to produce even better results. So we go to the next subject, which is RIS. Now, what is RIS? It's basically a potential solution for non-line of sight communication. As you can see, there is a transmitter, which is access point, and there is a user, which is UE, and there is a blocker between the two in line of sight, and the signal reaches the UE through a reflector, which is mounted on the wall. And this reflector is supposed to have reflection characteristics which are based on the unitary elements which are in the reflector, because reflector is constituted of so many unit elements, and those unit elements can be passive or active. Okay, there is no signal processing required for passive elements, and the signal quality or the signal power or amplitude or distortion, that depends on the size of the RIS, its number of elements it has, and of course its nature, active or passive, and how this RIS is illuminated by the signal which is coming from the transmitter. Okay, and we have more on that, and that is the next slide, which is here. So the trade-off between RIS size, the transmitter beam width, and RIS illumination density is what is you need to design for optimal performance. Optimal performance means the best signal you need that should reach the receiver. Okay. Now, this depends on whether the RIS is working in what we call finite regime or infinite regime, or if the RIS is working in near field or far field application. Okay, because it all depends on the distance, and you can see that there is in these graphs below. And by the way, these are all copied from this report. This work done by within the framework of WWRF by University of Piraeus. And you want to be more theoretical, we have even the closed form expressions for where this near field or far field regime start and how you can make use of it, and how you need to eliminate the RIS to make it work in finite or infinite regime. So that we have closed form expressions. So all this is available in this report. And what it says is that it depends. You can see here the RIS, which is a small size RIS, is eliminated nearly completely by the incident beam. So here it is not completely eliminated, but it is well eliminated. Okay, and here it's a big RIS, and it's only central part of the RIS that is eliminated. So here we are going from finite regime to infinite regime. And when you have the distance between the transmitter and the reflector and then the receiver, which is within this distance, within the near field distance, the behavior of RIS is different in the far field. Okay? The near field operation is happening in what we call with a spherical wavefront. Okay? And the far field behavior is more with the linear propagation, linear wave. Okay? So, we can make use of all these things, and RIS can be used to do not only beam steering, but it can be used even to do beam focusing. And it is possible that people have been talking about bending and self-healing beams. And all this information is once again included in this report from ITU, as well as it is available in the University of Piraeus examples. And I know that they have been working in these projects, which are Terra Nova and REA10, and there is one project in which they are working in collaboration with Marco Di Rando, Supelac, and François Batelli in IMT and links. Okay, so all this information is sort of public, and again there are no mathematics. There is no mathematics here, and these reports, there is no mathematics, but you have internal reports which give you even the closed form expressions for all of these. Okay. Then once again, all this is not because I have seen in one of the recent exhibitions in Paris that they have a demonstration. Actually, I think this RIS is made by a company in France, which is called Greener Wave. Professor Matthias Fink perhaps would have been here, but this is a demonstration which was set up by a Korean company, Taiwanese company, sorry, and they are showing like line of sight. I mean, this is the transmitter, this is the receiver, and what they are showing is that the transmit beam is directed to the receiver beam, and they are transmitting a signal in 100 megahertz bandwidth for transmitting a 256 QM modulation. So it's a very high bit rate transmission, and it is working in 26 gigahertz. And I have seen this demo. Of course, you block the signal, you see that this whole constellation disappears. I mean, it's real. They are doing it, but what they do is they do the modulation at 2 gigahertz, and then they transpose it at 20 to 26 gigahertz, and that's where the RIS is operating. And the RIS is being driven by a simple algorithm, which is it switches on and off certain elements. And all these algorithms, I think, are have been developed by this company, Greenerware, and I think this is coming from this Professor Matthias Fink. He is supposed to be a well-known figure in this work, and so this is once again, it is real. But all of what I have seen and all of what people have been working on, most of the time, is saying that you have a kind of line of sight channel between the transmitter, the RIS, and a line of sight between the RIS and the receiver. But in real world, in the mobile communications especially, it is not true. Dimitri, he presented something which is in a real world, but I don't know how far they have gone. But what I've seen, there is another analysis done by somebody working in WWRF also. It's a colleague from Nokia, also retired like me, but he's working, he's doing some work. So he has made very basic calculations starting from electromagnetic theory, that if you have the multipath propagation, the effective bandwidth which a RIS can handle is much less than the bandwidth of 100 gigahertz, 100 megahertz of signal which you require. Okay, and that is because there is constructive and destructive and non-destructive interference in multipath channel. And basically, if you want to design a RIS with very large bandwidth, to handle very large bandwidth signal, you have to have very long delay lines, and that doesn't seem to be so practical. So, once again, whatever has been shown in experiments and in theory, there is a certain, I would say, a school of people who believe that it's not going to happen like that in the real channel. But how much of multipath we are going to experience in a real mobile channel where we are going to apply RIS, that remains to be seen. So, just to tell you that there are all these big, huge technologies which are being talked about in the world, and there's a lot of hype, as you can say. There's a lot of work going on in the RIS, and maybe we'll see some presentations from our Indian colleagues also on this work. But this is a caution. I mean, for me, it's not yet solved, and that is one of the reasons, perhaps, I'm not sure, that, for example, in XC, in 3GPP, they have said that, okay, we are not going to work on standardization of RIS so far, because it's not yet fully known what is happening. In India, there is a body called TSDSI, there is an SEO. They have started working on a standard how to use RIS in a mobile communication system. And there is something called a standard on RIS in India, in TSDSI. But in ETSI, in 3GPP, they are yet thinking about it. But there is a lot of work, of course, there is a lot of publications, a lot of patents and so on. And just to sell my soup, I mean, it's all included in ITU reports also. Okay? The next subject is NTN. Of course, you have HAPs, you have LEOs, you have MEOs, and then you have GEOs. And I believe that you understand this diagram is not to scale, because we are talking about LEOs 600 to 1200 kilometers, and for GEOs we are talking about 35,000 kilometers. Okay, but this is seen that many people are working on NTN and with all the different orbits of satellites, and different orbits will be put to different applications usage. But the biggest problem is to be able to provide connectivity for the unconnected. And just to, just read out what is written here, that this is multi-constellations using diverse platforms. And of course, the onboard hardware, there are transparent and non-transparent satellites, and the onboard hardware can be transparent or regenerative, and regenerative payload can be done with the CUD split. And of course, if you want to connect different satellites, you need free space optical links. All these things are being studied quite at length, and there are people who are working to make sure that we have a standardized system so that we provide communication to terrestrial users, direct device to satellite communication, and we provide communication and broadband coverage to people in the aeroplanes, and they want to have a seamless connectivity as you are moving from terrestrial to network to non-terrestrial network. The user keeps on its call, and then there are various problems related with mobility management, and it has to be compatible with 5G, and it is going to be used for vehicular communication as well as for on-sea communication. So all these problems are still very much under study, and there is, for example, a team in Virginia Tech who are talking about the design of 3D cellular networks. And I met a young colleague who is working here with François Bacheli, also on 3D networks for the application of NTN and doing obviously stochastic geometry for 3D networks in cellular. That is going to be essential for NTN. Okay, the reference from where I take this schematic is also given at the bottom of the slide. Okay. Now, it is interesting, first of all, because, for example, if you take the LEO channel is characterized by several things. Of course, the attenuation, the pass off in the LEO channel varies with the orbit height, and it depends on whether you are working in what is called FR1 and FR2 bands, or it depends very much on the satellite elevation, because when the LEO satellite is moving, it depends at what angle is the user at the ground with respect to the satellite. So the satellite elevation determines the distance, and it determines the pass loss which the signal is going to experience. Okay, and then there is a variability in the channel, like elevation and mean pass loss are changing, as we have explained earlier. Dispersion now around the mean pass loss is there because there can be some shadowing objects, and obviously with the LEO satellites, there is a relatively large variation of Doppler which the receiver is going to experience. Okay, and that depends on the frequency of usage, and that depends on, once again, the elevation angle and so on. But all these things have been very well studied. It has been shown by simulation, which are done within the framework of 3GPP, that basically there are no showstoppers, basically technical blockage points, so that a user can directly work with a LEO satellite with a handheld terminal. All these things are available. Of course, the amount of bit rate and all those things that need to be done, but there is a basic clear picture on the feasibility of use of LEO satellite for NTN and direct communication between a terrestrial user and a LEO satellite. So it seems quite optimistic, but there is a lot of work that still needs to be done, because there is a lot of standardization work going on in ITUR WP5D, and then there is another group called WP4B, okay, because 5D takes only care of, is supposed to take care only of the terrestrial network, and it's only 4B which can handle the satellite part. So these two working groups are working together, working parties are working together, and there has been a lot of work already done in standardization as far as the modification or enhancements required for random access and discontinuous transmission and HARQ. Use of HARQ is concerned in LEO satellite. I guess people who work on these things, they understand that because of the long timing advance that you need to maintain, the random access protocols have to be modified, especially because if this timing or distance is varying for the LEO satellite between the handset and the satellite, then you need to have a random access protocol with the right timing advance at the time at every time, which is going to vary and depending upon the user location. Okay, same thing applies to HARQ. I mean, more you have delay in HARQ, more you have impact on latency, and if you have impact on latency and you want to satisfy all those stringent specifications of 0.1 millisecond, then you have to make sure that the mechanisms are designed correctly. And there is a work going on in the modifications required for reducing protocol, PDCP and SDAP. I leave the details. And then the biggest problem is when you want to do a seamless integration between T and terrestrial and non-terrestrial networks. There is a severe problem of mobility management, both in the ideal mode as well as in the connected mode. And that is because a single satellite cell would cover multiple terrestrial cells of the same network or even of different networks in different countries. So when you are talking about mobility management and you are talking about authentication of user, then you have to take into account all these different problems, and that's still not totally handled. It's still not yet standard. And then there is another point which is very important here, is that we need to have algorithms of dynamic spectrum sharing so that the same spectrum can be eventually used for satellite and for terrestrial communication. Same or different, but in any case, even if we have coexistence of different networks, we have to make sure that these different arrangements for dynamic spectrum management exist. Okay, and it is still a subject of research. just to finish with this thing I have already said. I mean, work done in 4D, in 3GPP, WP 5D, and WP 4B, and for the standardization. Now, just some discussion. Like if you want to have a real good operational NTN, providing the connectivity to unconnected, which are not always very rich people, you need to have a UE, user equipment, which is affordable. Okay, and getting a affordable equipment for user is better if you have economy of scales. You can have economy of scale if you have a standardized system. Okay, now 3GPP and ITU and the world over, people are working to make a standard for NTN and integration of NTN into terrestrial networks. Okay, because they want to get all these advantages. Okay, and at the same time, we have so many what we call proprietary systems, satellite systems, like LEO system. There is Starlink, OneWeb, and there is no interworking, there is no international roaming, and those equipment are usually proprietary and expensive. And I don't understand why, for example, the Indian government, they have very recently permitted the use of Starlink in India. Okay, and Starlink is a proprietary system. Elon Musk, the equipment sell for a very high price, and India, they have ISRO. I mean, they have all the expertise, but I really don't know why they, in the end, have accepted the use of Starlink in India. But at the same time, the TRI, the Regulation Authority of India, they have sent out a consultation for identifying spectrum for civilian satellite usage in India. And I think there is something called Indian Satellite Association or something. There is a body who is supposed to be handling all this business. But once again, I really don't understand why we are going away from the standardization. Of course, it will come only after some. So the last subject, and after that I stop boring you. So it is AI for AI. Today what is happening is that the different transmitter and receiver block, they start evolving step by step. That means you enhance or you replace the different processing blocks in the transmitter with ML, and then there comes a time when you regroup a certain number of blocks and you handle a group of blocks with ML, you replace that. And now people have been talking about, and it is nearly there, that the air interface would be partially designed online using ML. Okay, so this is the step-by-step process, and people are already in the research domain in this particular step. And that's what they think, that in 6G we are going to be having an automatically adaptable interface, air interface, native, that has certain advantage. Okay, now, so a better picture of that is that you have transmitter with the neural network and other transmitting blocks, transmitter blocks and receiver blocks, which are not using AI or ML, and you have the receiver also with the neural network. Okay, most of the receiver functions are grouped into a neural network. And of course, all this channel identification and happens with the online performance and the complexity we are talking about is very, very high. The other problem and is extremely high. I mean, but this is already done. And this schematic I've copied from this company called Viavi. I don't know if you have, they have a research center in UK and it is their schematic and they have already done this. And everybody agrees that the complexity is very high, but the ultimate that is going to come is that online operation, the receiver and transmitter will decide, depending on the channel conditions, what is the modulation, what is the constellation, and what is that we have to use. And this work has been done by this thing called this guy called Jacob Boydis, who was earlier in Bell Labs. He is working for NVIDIA now, and another guy in the US called Tim O'Shea, and all these publications are available, and they show that if we design these funny constellation online and certain channel conditions, there is a gain of 2 to 3 dB available in the link budget. Okay, and at the same time, this constellation design takes into account the imperfections of the hardware. Like Dimitri was talking about the pre-distortion in power amplifier, PAPR problem in power amplifier. All these things are taken into account already in the design and online adaptation of this protocol, this constellation, which is supposed to provide a link budget gain. Once again, the complexity is enormously high. And for example, this guy, Tim O'Shea, has been working on the automatic design of MAC protocols, but we are just in the beginning of the research of these machine learning and AI-driven air interface. I don't think it is going to come tomorrow, but it's already shown to be feasible and used. Okay? Now, when we are talking about AI, you can't forget about, for example, the LLM, because so far the LLM are being used only for using doing chatbots, user assistance, and people are talking about using LLMs for the configuration and operation and maintenance of the network, because the networks, bigger they become, more complex they are, and it is very difficult to tune those manually. So people are trying to, but it's still a very open research subject. And ITU, they have just established, that was 1 week ago, a focus group on artificial intelligence native for telecommunication network. Okay, and there are so many organizations like AI Forum, which is a vendor organization which is working on the subject. There is a drive to be able to use AI and LLM for real operation of telecom networks, but so far, I think, at least to my knowledge, we are really very far. Okay, and I'm done with this, and I'm not going to talk about other things, but it doesn't mean that Open RAN or softwareization of network is not important, but it is too much. I mean, it's already quite a lot, and ITU is working mainly on these things which I have told you. And in addition to whatever I've been telling about standardization, ITU is involved in something else in which the WWRF is participating quite a bit, which is the evaluation of the air interface technologies. And in 5G, they established different documents, a vision, then a KPI, list of key performance indicators, and then there is a method to do the evaluation to show that these key performance indicators are met with that technology or not. Okay? And this is the process or the reference for documents which were used in 5G, and same thing with the different documents is being done in 6G. Okay? And the evaluation work is done by many people. There is a Indian TSGSI has a team who does, and there is a Indian evaluation group, and which make contribution to this process in WP5D. The WWRF evaluation group, then there is a French Japanese and a Canadian and a Korean evaluation group. I don't know if there is a French evaluation group or not, but in India they are quite, TSDI has been quite active. Okay? And then, I'm sorry, as they say in French, I have to sell my soup, you know. So, I'm representing here WWRF. WWRF is an organization which is controlled by its member, and there are industry and academia members. And I won't bore you more. And we have like working groups, and we hold meeting. And here is a list of partners. Yeah, here is a list of partners from different academia in the different parts of the world. We have people from Australia, from Europe, everywhere, UK. There are partners in France, but not too many. And then there is a big thrust in India. I mean, in India we have IIT Madras, who has been a partner, member since 2002, and several times we have had people from a team of Giri Giridhar and Radhakrishna Ganti coming to our meetings, and those are, if students come to our meetings, we get student grants, and of course they can have their publications also. And then we have IAC member is recently become member. It's a provisional member. It is Professor Jim Curry, and then we have BITS Pilani Hyderabad campus, who are member also. And our next meeting in February 25 is going to be hosted by BITS Pilani Hyderabad. That is an information for all of you guys. MNIT Jaipur is a member, Amrita Vidyapeeth Bangalore is a member, and IIT Guwahati, thanks to Kuntal, we have one more member from India. And then there is, of course, TSDSI and WWRF collaborate quite a lot in the evaluation of HMT 2020 technologies and so on and so. So if you are interested, I can talk to you more about those things, but I'm sorry to bring in this. But in France, we have to, we say that we have to sell our soup also. Okay? Thank you very much. And if there are any questions, I will be more than happy to answer.
Long live India and France friendship.